Today we're going to do a quick run through of electron configurations. Let's get started. Let's start by talking about the general definition of orbitals. So what are they? They're described as the shape or pattern of electron density of an atom. There are 4 different orbitals, each with a different shape, but I'm not going to talk about that in this video. What we need to know are that there are 4 orbitals, and they are s, p, d, and f. Red is representative of s orbitals, so helium is a part of the s orbitals as well. Blue represents the d orbitals. Yellow represents the p, and green represents f orbitals. So how many electrons fill each orbital? For s, it takes 2 electrons to fill, p 6 electrons, d 10 electrons, and f 14 electrons. Now that we have the basics out of the way, let's talk about how we write electron configurations. The format for writing electron configurations is a period number, followed by orbital and a superscript. This period number is a period number for the s and p orbitals, but for d and f, we can consider those as the preceding number before the orbital. So right here we write the period number, which is going to be depending on which period the element of interest is going to be. So let's say our element of interest is calcium, so the period number is going to be 4. But there are exceptions to this rule, which is for d and f orbitals. To find this number, which is not exactly the period number, it's the preceding number preceding the orbital, which is written in this format. For d, it's the period number minus 1, and for f, it's period number minus 2. So if we were to ask for the number preceding of, let's say, Einsteinium, which is going to be in, there's going to be a position right here. So the stars align with the other stars here. So this part of the periodic table, the f orbitals, get inserted in between the s and the d orbitals from period 6 and 7. So as we know, for f, it's going to be the period number minus 2. So 7 minus 2. And so we know for Einsteinium, it's going to be, the number preceding is going to be 5. And for something like titanium over here, which is period 4, we know that d, the number, to find the number preceding the orbital, it's going to be the period number minus 1. So 4 minus 1 is 3. Now for the orbital, it's going to be a letter, either S, P, D, or F. The superscript represents the number of electrons filled, and I'll go into more detail about that. Okay, as we know, the superscript represents the number of electrons filled. To find this superscript, count numerically from left to right within a period and orbital to find the number. So let's say we're focusing on period 1 here. So we know that only s orbitals are in period 1. So what we do is count from left to right. So there's 2 elements within period 1 and an orbital in s orbital 1. So therefore, we just count from left to right. This is 1, this is 2. And so if we were to find the superscript for helium, it would be 2. And for the overall configuration for helium, it would be 1, which is the period number, s, because it's in the s orbital, and 2. Now, let's take, for example, hydrogen. And let's go back to the periodic table and try to figure out the configuration. So for hydrogen, as with the example with helium earlier, we know that the format for writing electron configurations is the period number, or the preceding number. So I'm just going to put that as a hashtag for period number. Okay, and the orbital, followed by a superscript, which represents the number of electrons that are filled by the orbital. And so for hydrogen, we know it's in period 1. So therefore, we can write down 1 in front. We know that it's located in the s orbital, so s, and we can count from left to right to figure out the superscript, or the electrons filled. So this is 1, this is 2, so therefore, this is going to be 1. 1s, 1. And that's the electron configuration for hydrogen. So what we've done so far is write simple electron configurations, like from period 1. Now, to write out the full electron configuration for more difficult elements, we must go from left to right across a period, writing the configuration out, and jump to the left-hand side as if we were reading a book. And this will make more sense with an example. So let's just try to figure out the electron configuration for fluorine. Let's not go look underneath there. Okay, so fluorine. This is our element of interest right here. Okay. So we know that we have to read this like a book. So we start at hydrogen. That's always going to be our starting point here. And once again, we know this is in the s orbital in period 1. So we can write 1s. But we must, before moving on to the next period, we must fill this group first. So it's going to be 1s2. So we complete this entire period here. Then we can start at period 2 and move on through. Okay, so now we move on to the second period, 2s2, because there's 2 electrons filling the s orbital here. And in order to get here, we must go through the p as well. So 2p, 5, because we can count 1, 2, 3, 4, 5. It gets a little more complicated when you incorporate d and f orbitals, but it should be the same type of technique to it. Except we just need to keep in mind that d orbitals are, like the number preceding, it's going to be the period number minus 1. And for f, that preceding number is going to be period number minus 2. Here I have 2 practice questions that you can solve, and I will reveal the answer to them in 5, 4, 3, 2, 1. Okay, let's solve Einsteinium together. So as we know, we need to read across a period and move on to the next part on the left side, next period, as if we're reading from a book. So from left to right, like reading lines from a book. So now let's start with hydrogen. So that's going to be 1s1, and if you incorporate helium, it's going to be 1s2. So 1s2, and we finished the first period. 2s2, we finished this part right here. And then there's 2p6, we finish this category. 2p6, 3s2, we completed that. And then we arrive at 3p6, so 3s2, then we got 3p6, then 4s2, we completed this fourth period. And then now is where it start getting tricky. So this is D, so we got to remember it's the preceding number is going to be 4 minus 1, so it's going to be 3. And then to complete a D, we know that 10 electrons fills it, so 10. And then we move on, after completing this entire row, or this entire period, we move on to 4p6. And I'll get back to you once I get to the f orbitals. Okay, now we have arrived at 6s2, which is right here. And so we see the star here, which means that we need to push this entire f orbital up to here. Same with this right here, up there. So now since this goes up here, it's in period 6. To find the preceding number for the f orbital here, it's going to be group period number, or period number, minus 2. So 6 minus 2, which is equal to 4. It's going to be 4f, and we might as well just calculate the next one, which is going to be 5f, since it's 7 minus 2. Okay, now that we've gotten to that point, it's going to be 4f, and we know 14 electrons fills that, and then we can move on to the d's right here. So it's going to be 5d, 10, 6p6, 7s2, and now the 5f. And Einsteinium, it's going to be right here, so we have to calculate how many electrons fills that. So we know this is 14, we can just count back, 13, 12, 11, so 5f, 11, and that's it. We've written the entire electron configuration up to the point of Einsteinium, and that is the full way to write electron configurations. And as you saw in the Einsteinium example, it's really difficult having to write out the whole configuration, especially if the element is near the bottom right of the periodic table. So the solution is to use noble gas notation, and that's the easy way to write it. So let's take, for example, Einsteinium. As you saw, we got this whole mess right here. So instead of writing it starting at hydrogen all the way down to Einsteinium at 99, instead we can start out by skipping to the noble gas, the period above the element. What I mean by that is this Einsteinium is going to be located in period 7. So ignoring that this number is going to be used as the electron configuration preceding number, we can look at the period number here. So it's 7. So Einsteinium is located on period 7. And the noble gas, the period above, is going to be radon, since this group 18 is the noble gases. And so, but instead of starting at hydrogen, we can start out at radon. And in order to write out the configuration, all we need to do is put radon in brackets and proceed from there. 7s2, and as we know, the stars need to match, so this entire F category needs to be pushed up in between the 6s, 7s, and 5d and 6d categories. So since this is going to be in between, we just count from 5F, and we find that this is the 11th element within the F category, so it's going to be 5F11. And that's it. It's that simple, using noble gas notation. There are certain exceptions to writing out electron configurations, but I'll leave a comment down in the description, as there are only a few exceptions that you need to know. Well, and that's pretty much the video, guys. If you found this video helpful, leave a like, comment, and let me know if I made any mistakes, as I'm still learning how to do this whole YouTube thing myself. Thank you.